In section 13.10, we're going to talk about an application of the gradients, which allows us to find optimization of particular problems called the Lagrange multipliers. So constrained optimization is quite heavily used in real-world applications, and this is helping us look for minimums and maximums, but oftentimes when we're looking for those minimums and maximums, we're looking for them under constrained scenarios or conditions. For example, in economics, when we're talking about production and manufacturing and capital and stuff like that, often that is constrained under, the business's financial models and such. And so we have economic equations that allow us to model manufacturing, but then we have to take into account that there are constraints on those productions. So these constraints tend to complicate the problem, but they do make the answers that we arrive at more applicable to the real world. So let's look at a non-real, I guess it's a non-real world example that I would say. It's kind of one that helps motivate this idea, but rather in an abstract way. So say you want to find the rectangle with the maximum area that can be inscribed in the ellipse that looks like this. So if we're just quickly kind of drawing, not very greatly to scale, we're going to have kind of this ellipse like that. I mean, that's very poorly drawn. But what we're trying to find, let me get a different color here. What we're trying to find is the rectangle that we can inscribe inside of here that is going to have the maximal area. Well, if we look at it kind of in the first quadrant, then the length of this, that would be like y. So the total length would be 2y, whatever it is we choose. We have to imagine like this is a sliding point that can go. And so as we slide down, I really hate how bad this drawing is, honestly. But let me move. So coming back here, we want to find the rectangle with the maximum area. So as I described, our sides are 2x and 2y. So the total area would be 2x times 2y, so that's going to give us 4xy. So this is our function of our area that we're trying to maximize, but we're constrained to be inside the ellipse. Okay, so this is actually our constraint. And this area is what we're trying to maximize. Now, all the possible values of the area make up a family of hyperbolas. So, for example, if I said, okay, 4xy equals some constant k, then notice this is like saying y equals that's y equals k over 4x. So that's a family of hyperbolas. So this is a bunch of level curves. So the total, all of the possible areas, even the ones in between whole numbers, like all of the real numbers values here for these level curves, make up a family of hyperbolas. Now, the level curve that is going to sit on the boundary of the ellipse, that is tangent to the ellipse, is going to represent that maximal area. So let's go back to the next slide and look at that. Forward and point at this one so we can see. So we have this kind of inscribed rectangle here, but we have to imagine that kind of these points here on the corners are kind of movable. So for example, if I made this a corner, we would get a different type of rectangle with a different area, and so that's adjustable. So the question is that we're trying to figure out is which rectangle has the maximal area. So here we have this slide that shows right here are our level curves, those different values of k, and we can see right here on this particular value, that is our tangent level curve. Now, how are we going to tie that to the gradient? Well, remember, every level curve has gradients that are normal to it. And so if we can find the gradient of the ellipse function and then the gradient of these level curves that are tangent, and they're going to be tangent when they're parallel, then we will have found the solution that maximizes this particular problem. So that's what I've written here. So we want to find the appropriate hyperbola analytically, and using the fact that the two curves are tangent when their gradients are parallel, that's saying that we find the gradient of f and multiply it by this lambda times the gradient of g, where we call this lambda the Lagrange multiplier. Okay, so it's kind of going to help us narrow down to the multiple of the gradients that are kind of in the same direction, so they're tangent to each other. All right, so this is the equation when we're talking about one constraint. I'll write that down. One constraint. We're talking about lambda. That is our one Lagrange multiplier. All right. So let's go through the analytical process of finding the optimization. So our area function fxy is equal to 4xy, and then this is going to be sort of our gxy. Again, it's best to think about this set equal to 0 because we're finding the gradient. But since we don't have a z in this case, we're kind of okay not worrying about it. I would prefer to go ahead and write it as x squared over 9 plus y squared over 16 minus 1. So we're looking to solve the equation gradient f xy equals lambda gradient g xy. So that's going to be 4y and then 4x equals lambda times, and then the gradient of g is going to be 2x over 9 and then y over 8. So this is actually going to give us three equations. It's going to give us 4y equals 2x over 9 lambda, 4x equals y over 8 lambda, and our constraint equation x squared over 9 plus y squared over 16 equals 1. So I'm going to move over here. So what we want to do now is we want to figure out a way to eliminate lambda. So for example, in this first equation, if I solve for lambda, I'm going to get, so that's going to give us 9 times 4y divided by 2x, so 2, and so we're going to have 18y over x. Now, substituting that into this, we're going to have 4x equals y over 8 times 18y over x. So if I multiply the x over and then divide the 4 over, I end up with x squared is equal to, and that should give us 9 over 16y squared. So that's going to give us, we've eliminated lambda. Just highlight this equation. We've eliminated lambda. So that's going to give us the power of substituting this x squared into this equation. So now we can say that's going to be 9 over 16 y squared times 1 over 9 plus y squared over 16 is equal to 1. So the 9's cancel, and we're going to have 2y squared over 16 is 1. So y squared is going to equal 8. So y is going to be plus or minus 2 square root of 2. So we now have a y. Now, since we're talking about length, we can just go ahead and use 2 square root of 2, since we're talking about the length. So for x, so x squared, now that we know that y is 2 square root of 2, x squared is going to be 9 over 16, 2 square root of 2 squared. So x squared is going to become, so that should give us 9 over 2. So that should, because that should be 9 times 8 divided by 16, or, yeah, so that'd give us 9 over 2. So we can write x as 3 over, it's going to be plus or minus the square root of 2, or plus or minus 3 square root of 2 over 2. But again, we can use the positive one. So we know that y is 2 square root of 2, x is 3 square root of 2 over 2, and that is going to lie on the area function. So 3 square root of 2 over 2, 2 square root of 2 over 2. If we multiply that out, we should get 24. So that is going to be the maximal area inside of the ellipse, and the rectangle's sides that fit that maximization are going to be 2 square root of 2 and 3 square root of 2 over 2. So if we go back to that image, which I can't really using this slide software, if we were to go back to that image that showed the ellipse and the level curves, we found k equals 24 is the one that sat tangent to the ellipse and the family of hyperbolas, which were the level curves. So that's the idea of Lagrange multipliers. Kind of zoom out so we can see the full slide here and what we did. But it all really starts under one constraint, with this equation for the Lagrange multipliers. So let's look at an example from business. Again, we've talked about this before in the class. It's called the Cobb-Douglas production function, which looks like this. And we had, it was a constant with x to the alpha, y to the beta. So this is the Cobb-Douglas production function. So here we're talking about x is the units of labor at $150 per unit, and y is the capital at $250 per unit. We want the total cost of labor and capital limited to $50,000. We want to find the maximum production level. So in this case, our f of xy is given. So y to the 1/4. And then our constraint equation is going to be, because we're constrained to be the labor, which is going to be $150 per unit x, plus the capital, which is going to be $250 per unit y. The sum of those two cannot exceed 50,000. So we'll just say equals 50,000 is what we want. That's kind of on the boundary, the best that we can have. So this is our constraint. And then this is what we're wanting to maximize. The book calls it the objective function. So the objective function. So with Lagrange multipliers, our goal is to solve this equation with the gradient of f and g. So the gradient of f is going to be, if we multiply that out, that's going to give us 75x to the negative 1/4, y to the 1/4 in the x position, and then for the y, that's going to be 25x to the 3/4, and then y to the negative 3/4 is equal to lambda times. And then for the x and y, those are kind of nice. That's going to be 150 and 250. So our three equations, remember we get three equations with one constraint. So we've got 75x to the negative 1/4, y to the 1/4 is equal to 150 lambda. And then we've got 25x to the 3/4, y to the negative 3/4 equals 250 lambda. And then we had our constraint equation of that. So think about this is kind of the quote-unquote system we're trying to solve. All right, so here's that work. I just moved it over to a new slide so we have some more room. So again, we want to kind of eliminate lambda. So in the first equation, if we solve for lambda, we end up getting so 75 divided by, okay, so that's going to be a half. So we'll end up getting lambda equals x to the negative 1/4, y to the 1/4 over 2, just dividing both sides by 150. And then substituting that into the second equation is going to give us 25x to the 3/4, y to the negative 3/4 equals 250 times x to the negative 1/4, y to the 1/4 over 2. So by some simplification, let's see, if we multiply both sides by 1/4, or x, so like multiply this times x to the 1/4, and then this times y, I would say to the negative 1/4, just to move x and y over. We'll see, just see what's happening. And then this is going to be 25, so that's 125. And so we multiplied this side, we'll multiply this side. Oh, this is getting cramped. So let's just write it like this. We're multiplying everything by x to the 1/4. So over on the left-hand side, if we multiply here, if we multiply x to the 1/4, that's going to give us 25x. If we multiply y to the 1/4, that's going to give us y to the negative 1. And then, like I said here, we're having that equal to 125. And then x to the negative 1/4 times x, that kind of, the point of that was to cancel it. And then y also cancels. And then we can divide both sides by 25 as well and move the y over. So x is equal to 5y. So I did that by multiplying both sides by 25. 125 divided by 25 is 5, and I multiplied both sides by y to get rid of the -1. So x is 5y. Well, that's great, because remember, we're constrained to 150x. So I'm going to replace x there. So 150x is 5y plus 250y is 50,000. So that's going to end up giving us, what's that, 1,000 y over on the left. So y is 50 units of capital. And since x was 5 times y, that's going to be 250 units of labor. So the production level that's maximized is going to be 100 times 250 to the 3/4, and then 50 to the 1/4, which is about 16,719 units of production. So that is our optimization under that constraint. So just zoom out on this to give us a look here. Again, the hardest part, I would imagine, for most people is going to be going from the system that we have and then eliminating lambda. So eliminating lambda tends to be kind of the kicker. This is one of the harder parts of these types of problems. But if you like systems of equations and you want to get familiar with them, these are great problems to do that. So let's look at one where we have 3 variables, but we still only have a singular constraint. So here we've got 3 variables, but we're still constrained to one equation. We're just going to jump in. We're just trying to solve f of x, y, z is equal to lambda g of x, y, z. So on the left-hand side, we're going to have 4x, and then for y, we're going to have 2y, and then we're going to have 6z. So that's going to be the gradient of f, and then lambda times the gradient of g. Now again, I would kind of hearken you to remember that this is, kind of under the conditions that it's equal to 0, but it's not consequential here. So it's going to be 2, -3, and -4. So we're going to have, this time we're going to end up with 4 equations. We're going to have 4x equals 2 lambda, 2y equals -3 lambda, 6z equals -4 lambda, and then our constraint equation, 2x minus 3y minus 4z equals 49. So again, eliminating lambda. So we divide both sides by 2, we'll have 2x equals lambda. So replacing that in here, 2y equals -3 times 2x. So that's -6x. So that tells us y is equal to -3x. And then here we're going to have 6z is equal to -4 times 2x. So 6z is equal to -8x. So z is going to be, if we divide both sides by 6, that's negative, and then divide by 2, 4/3 x. So that should allow us the substitution of 2x minus 3 times negative 3x minus 4 times negative 4/3 x equals 49. So 2x plus 9x plus 16/3 x equals 49. So what I've done here is I've multiplied everything by 3 to get this equation, and this ends up becoming 49x equals 147, so x is equal to 3. And then we're just going to work our way backwards. So z is equal to negative 4, and y then is equal to negative 9. So that solves the little system of 4 equations and 3 unknowns. I guess it's 4 equations and 4 unknowns, well, just eliminating lambda. So from there, we can plug back into our original function, our f function 3, negative 9, and 4. And what we end up getting is 147. So the minimum value of this particular 3-variable equation, or that would be some kind of hyperspace equation, under this constraint is 147. Now, in the 3-variable case, we're talking about where level surfaces are tangent, and it's a little more difficult because, again, it's hard to graph those things, what we're talking about. But it is kind of where the gradients are still equal, which is a nice trick. So what about if you have 2 constraints? So what if you're more constrained in your optimization problem? Well, you just introduce another Lagrange multiplier. For these particular problems, we typically introduce mu. So we have lambda and mu as our Lagrange multipliers. So let's look at our last example. So we've got the temperature equation here, represents the temperature at some point on the sphere. We want to find the extreme temperatures on the curve formed by the intersection of the plane and the sphere. Okay. So we're going to start with our 2 constraint equations. So g of x, y, z is going to be x squared plus y squared plus z squared minus 11. And h is going to be x plus y plus z minus 3. So that's our 2 constraint equations, and then our t equation is kind of like our f equation. So this is like our f. So gradient of t, x, y, z, is going to equal lambda g x, y, z plus mu h x, y, z. So this is going to be, so for x, it's going to be 2, and then 2, and then for the z position, 2z is equal to lambda times, and then for g, it's going to be 2x, 2y, 2z plus mu, and then for h, it's going to be 1, 1, and 1. So we have 4 equations. We have 3 variables plus lambda and So let's look at what we've got. We've got 2 is equal to 2 lambda x, or, yeah, 2 lambda x plus mu. We've got 2 equals 2 lambda y plus mu. We've got 2z equals 2 lambda z plus mu. And then, of course, we still have our x squared plus y squared plus z squared equals 11, because we're still constrained to the sphere, and let me fix that too. And we still have x plus y plus z equals 3. So we can, if we look at subtracting these two, it does make our system a little simplified. So if we subtract straight down, that's going to give us 0 equals, and then these are both have 2 lambda in it, so if I factor that out, we get x minus y, and then the mu's cancel. And so then we have the equation 2z equals 2 lambda z plus mu x squared plus y squared plus z squared equals 1, and x plus y plus z equals 3. So we have this little system now to concern ourselves with. And what we could do is we could actually rewrite this equation so it more mirrors what the first equation looks like. So that would be 2z 1 minus lambda minus mu. So from equation 1, we can gather that we're going to have two kind of possibilities, two branches, either lambda equals 0 or x equals y. So let's start with x equals y. And notice that in the bottom, that means that if we replace x with y or y with x, then we have like x plus z equals 3. So z is equal to 3 minus 2x. But that also means, so this comes from the fourth equation. So this is 4, 3, and 2. So from the fourth equation, and then from the third equation, that also means that z squared is equal to 11 minus 2x squared. So we can substitute once again. So we're going to have 3 minus 2x squared equals 11 minus 2x squared. So we'll have 9 minus 12x plus 4x squared equals 11 minus 2x squared. So if we get this equal to 0, it's going to be, let's write this where it's kind of in the standard form we would like. So we would have 6x squared minus 12x minus 2 is 0. So 3x squared minus 6x minus 1 is 0. So x is going to be 6 plus or minus the square root of negative 6 squared minus 4 times 3 times negative 1 all over 6. So 6 plus or minus the square root of 48 over 6. So that's going to be 6 plus or minus 4 square root of 3 over 6. So if we, that's divide everything by 2, 3 plus or minus 2 square root of 3 over 2. So then we need Z. If we work out Z, we end up getting that to be, well, so I'll leave it to you to continue down the path, but you've got the following points going down this path. So for x and y being 3 plus this 2 square root of 3 over 2, 3 plus 2 square root of 3 over 2, that ends up giving you a z of 3 minus 4 square root of 3 over 3. And then you also have 3 minus 2 square root of 3 over 2, 3 minus 2 square root of 3 over 2, and then you get 3 plus 4 square root of 3 over 3. So that's if you follow down the x equals y path. If you follow down the lambda equals 0 path, and I'm going to let you do that because I don't want this video to be overly long, then you end up getting the points 3, -1, and 1, and -1, 3, and 1. And then, so now we have 4 points for these two. If we plug them in, they both equal 25. And then if we plug in these 2 points that we had down here in the bottom, so if we have this, I'm just gonna, you end up getting the same thing. So if you do 3 plus or minus 2 square root of 3 over 2, 3 plus or minus 2 square root of 3 over 2, then you end up getting 3 minus plus 4 square root of 3 over 2. And that value is 91 thirds, which is about 30.33 degrees, whatever the temperature was. So under these two constraints, we end up finding both the min of 25 degrees, whatever the temperature is, and the max of 30.33 degrees. And that's kind of all for this. So I will leave you to it to work on your web assigns and look at the problems there and practice.